we are studying simple harmonic motion, which is the case of simplest case of harmonic motion, oscillatory motion. This is slinky and we have suspended weight here key. This is in equilibrium condition, and from equilibrium condition I am displacing downward, suppose A unit this way, and I am raising. It will oscillate, and we want to find periodic time t for this oscillation, and we want to find y, formula for the y in terms of time t. We have considered y equal to 0 is the reference level. Okay? Okay. Stop here. Now we are deriving the differential equation of simple harmonic motion and then after its solution. See, this one is the normal condition of the spring. This one after suspending a block, and when the block attains equilibrium condition, say this location has y equal to 0. Here the block is at rest position. Weight force is downward and the restoring force produced by the spring is in upward direction. And we know that restoring force is directly proportional to extension in spring. So suppose here the extension is delta L, so restoring force is K delta L. Here the block is in rest position, so K delta L must balances mg. Now from this location, equilibrium condition, it is y equal to 0. I am displacing the block further downward, say A unit, it becomes amplitude, and from this I am releasing the block. After that, block performs oscillatory motion. At certain instant we have taken photograph. Suppose at that instant block is at a distance of y unit in upward direction from y equal to 0. It may be moving at this location. So this one is delta L. So this one should be delta L minus y because of this one is y. At this location, what about the force acting on the block, net force? We want to find. So at this location, the extent of the spring is delta L minus y. The spring force on the block is in upward direction, having magnitude K into delta L minus y. Mg is always downward here. So we have taken minus sign here. So opening the bracket, K delta L minus Ky minus Mg. But K delta L is Mg. So these two terms cut out. So finally we got F equal to minus Ky. F equal to minus Ky, net force acting on the block. But we know that F equal to Ma. Ma is minus Ky. So M is d square y by dt square. Second derivative of position gives acceleration minus K. D square y by dt square is minus K upon M into y. Therefore, d square y by dt square plus K upon M into y equal to 0. This is the differential equation of SHM. Now we want to solve it, that is, we want to find the relation of y in terms of time t. Solving this differential equation, that is representing y in terms of time t. For this, we are applying trick to integrate it. Multiplying this equation, both the sides, by dy by dt. So, d square y by dt square into dy by dt plus k upon my into dy by dt equal to 0. 0 into n number is 0. Now taking integration with respect to both the sides. So integral both the sides, integral dy by dt, d square y by dt square dt plus k upon m integral y dy by dt dt equal to integral 0 dt. we can adjust this way. Integral dy by dt raised to 1 into d square y by dt square dt plus k upon m integral y raised to 1 dy by dt dt. And we know that derivative of constant term is 0. So integration of 0 is constant. We have taken c dash. Now, using the formula, just focus it here. One important result, integral f of x raised to n into f dash x dx. The answer is f of x raised to n plus 1 upon n plus 1 plus c, if n not equal to minus 1. And proof behind it, suppose f of x equal to t. Taking differentiation with respect to x both the sides, f dash x equal to dt by dx. F dash stands for derivative of f. Cross multiplication, f dash x dx equal to dt. So required integration, this f of x raised to n, but f of x is t, so t raised to n. F dash x dx is dt. And now the well-known formula, t raised to n plus 1 upon n plus 1 plus c, n not equal to minus 1. Now replacing t by f of x raised to n plus 1 upon n plus 1 plus c. We are using this formula here. Here it is dy by dt raised to 1 and this term is the derivative of this term. So we can apply this rule. So dy by dt raised to 1 plus 1 upon 1 plus 1 plus k by m. Here y raised to power 1 and this is the derivative of this term. So we can use the formula y raised to 1 plus 1 upon 1 plus 1 equal to c dash. So it is dy by dt square by 2 plus k upon m y square by 2, multiplying both the sides by 2. So dy by dt whole square plus k by m into y square is 2c dash, and take c, it is another constant. Now we know that at y equal to plus or minus a, that is at extreme location, downward location, and extreme upward, oscillator becomes momentarily stationary. So velocity is 0 at that location. So v is dy by dt is 0. Putting these values in above equation, this one is v, it is 0 plus k by m into y is plus or minus a whole square, but it is a square. Plus or minus a square is always positive, or it is c. Okay, so c is k by m a square. So this c is replaced by k by m into a square. Now this one here, dy by dt square plus k by m into y square equal to c, but c is k by m into a square. Readjusting the terms, dy by dt whole square is k by m into a square minus y square. So dy by dt is taking square root k by m into root y square minus a square. Sorry, it is a square minus y square. A square minus y square, a square minus y square. This one is a square minus y square. Readjusting terms, 1 upon root a square minus y square dy is root k by m into dt. For this, suppose y equal to sine inverse x and we want to find dy by dx, that is we want to find d dx of sine inverse x. But y equal to sine inverse x, the property of inverse trigo is x equal to sine inverse, because this is the reverse function. So dx by dy, we already know cos y, and cos y is root 1 minus sine square y. We have taken plus sign here because of in fourth and first quadrant cos is positive. So we have taken plus sign here. So dx by dy is root 1 minus x square. So dy by dx is 1 upon dx by dy and 1 upon dx by dy, 1 upon dx by dy is this. So d dx of y is sin inverse x, and it is 1 upon root 1 minus x square. So derivative of this is this, so integration of this is this. So integral 1 upon root 1 minus x square dx is sin inverse x plus c. So if 1 is replaced by a square, so integral 1 upon root a square minus x square dx is sin inverse x by a plus c. We will use this result here. So integral 1 upon root a square minus y square dy, root k by m is constant. So taking out of the sign of integration, integral 1 dt. The integration of this term is according to formula sin inverse y by a equal to root k by m into t plus phi. Phi stands for constant of integration. This time we have taken phi instead of c. Now again using the property of trigonometric inverse trigo, sin inverse y by is this. So sin of this is this. Suppose sin pi by 6 is half. So sin inverse half is pi by 6. Vice versa. So sin of root k by m into t plus phi is y by a. So y equal to a sin root k by m into t plus phi. Consider this function as f of t. We know that the principal period of sine function is 2 pi. So y equal to a sin. If we add 2 pi in this term, we get the same result. So a sin root k by m into t plus 2 pi plus phi. So a sin, taking common root k by m, we can say dadagiri common. So root k by m, here t plus 2 pi by root k by m plus phi. If this one is f of t, this must be f of t plus 2 pi by root k by m. So for any t, if we add this term, we get the same result. So this should be the periodic time t. So t is 2 pi root k by m. So root k by m is 2 pi upon t. T is periodic time t. So it is called angular frequency. It is angular speed also. Squaring both the sides. So k by m is omega square. So k is m omega square. Again this omega is 2 pi upon t and it is root k by m. So subtracting t, we get t is 2 pi root m by k. Okay. In our case, we have suspended spring in vertical direction. So we have doubt. There should be g, gravitational solution, in the formula of periodic time t. But here, finally we got periodic time t for simple harmonic motion is t is 2 pi root m by k. G is absent. So why g is absent? So here we are using energy balance. Energy of an SHO at y equal to y. Considering y equal to 0 as reference level. So energy at that location. At that location, the extension spring is delta L minus y. The potential stored in spring is half k into delta L minus y whole square. Plus at that location, block may be, SHO may be moving. So it has some kinetic energy half mv square. Plus mgy, gravitational potential energy. Okay, because it is at y location height from reference level, and y equal to 0 we have considered reference level. But for an ideal oscillation, that is no damping, mechanical energy, that is total energy, remains same by the time as well as at any location. So dE by dt should be 0. This term, derivative of this with respect to time t, should be 0 because of as a whole total addition does not change by the time. Now we are taking derivative with respect to time t. So half k delta L minus y whole square, the derivative of delta L minus y whole square with respect to delta L minus y is 2 into delta L minus y. But we have to take further derivative because we are taking derivative with respect to time t. So delta L is 0 minus dy by dt plus half m v square is 2v derivative of v square is with respect to v is 2v, but we are taking derivative with respect to time t. So we have to take further derivative dv by dt plus mg dy by dt is 0. 2 to cut out, this 2 is also cut out. So k into delta L minus y minus dy by dt is v, mv dv by dt plus mgv. These we cut out, dividing both the sides by v. So we get minus k into delta L minus y plus m dv by dt plus mg equal to 0. So opening the bracket and rewritten term, minus k delta L plus ky plus ma plus mg equal to 0. But k delta L is mg. We already discussed that. So this term cut out, minus mg plus mg. So f plus ky equal to 0. So f equal to minus ky. So ma is minus ky. So m into d square by dt square is minus ky. So d square y by dt square plus k upon m into y equals 0. There is no term connecting g here. So periodic time t does not depend on g.